All right, good morning, everybody. So today, what we're going to do is we are going to finish our discussion of splay trees, and then we're going to discuss a data structure called a treep, which is also known, which can be extended into a data structure called a probabilistic tree. So what I would like to show you first is, where are you? This file splaytest.cpp. And what we have is we have several insertions, and then I'm going to call check contains. And what's going to happen is when we call the contains method, that's actually going to splay that element or the closest element to the top of the tree. So very quickly, what I'd like to do is I'd like to bring up the visualization. And what we're going to do is we're going to go through the same insertions that are going to be in this example. And what I have in the slides are the results. It's going to be 12, 10, and 8. And so what's going to happen is 10 is going to go into the left, and that's going to splay 12 up like so. And then 8 will be on the left, and will splay up, and then 10 will become its right child. So that's going to be 13, 11, and 14. So 13 is going to be the right child of 12, and then it's going to splay up. So what's going to happen here is that 13 is going to become 10's right child, and 12 is going to become the left child of 13. And that's going to keep rotating like that all the way up. So let me bring this down just a little more. There we go. So I'll press pause, and then we're going to do 13, and it's going to go all the way down. And then it's going to rotate, and 12 is going to become the left child of 13, and then eventually 10 will be the left child of 13. So we see that that was our zig-zig to the right. And then it's going to rotate so that 8 will become the left child, and then 12 will become the right child. So just to go over again, what happens here is when we get to this stage, it hits this zig-zig right, and it's going to make 13 the root, and then it's going to rotate 12 to be the left child of 13, and then 10 to be the left child of 12 in the zig-zig. And then it will rotate like this. So then with 11, 11 is going to be inserted as the left child of 10. And so we're going to have a situation where we're going to have a zig-zig to the left. I'm sorry, we're going to have a zigzag to the left, excuse me. And so what's going to happen is that's going to rotate 11 up, so 11's in the middle. And then we have a zigzag left again. So 11's going to be in the middle. 8 is going to become the left child of 11. Right, 13 is going to become the right child of 11. And we see that the original children will move like that. So then we have 16. 16 will become the initial right child of 13. And we're going to have a zig-zig scenario. And it's going to rotate like that. Then we have 15, 7, and 9. 15, 17, 7, and 9. So we've got 4 more. So it's 15 is going to come here, and it's going to rotate up like so. 17 is going to become the right child of 16 initially, and we'll have a zig-zig to the right. And so it's going to make 17 the root, 16 its left child, and then 15 the left child of 16. Then we have 7 and 9. So this is kind of a scenario in which a split tree might have a trending worst case, but then we get a couple more insertions that will fix that. So 7 would step forward, and 7 is going to be all the way on the left. And so we have a zig-zig scenario. So 7 is going to move up to be in the middle of 8 and 11. And then we're going to keep moving these up like so. And then we're going to insert 9. And 9 is going to be initially the left child of 8. So it's going to come down like this. Sorry, it's going to be initially the left child of 10. I'm going to see the rotation here for the zig-zag. Then we have a zigzag, so now 9 is going to be in the middle of 8 and 13. Then we have a zigzag of 7 and 16, like so. So now 9 will be in the root. Its right child will be 16. 7's right child will be 8. And 8's left child will be 13. Yes? They're not really. The only difference is that the AVL rotations are localized to perform balance that checks the balance on each side. Here it just does it without checking any balance.
Well, I feel like in the zigzag rotations, it's not actually going in the middle.
No, in the zigzag, it doesn't go in the middle. In the zigzag, so let me show you an example here. So you're here, right? So what's going to happen is zigzag is going to move this guy up, right? What's going to happen is it's going to be 9, 10, and 11. So watch this here. So that's a little different than, see that? And then here we go to the next level. So this would be child, parent, and grandparent. And this is where we have a zigzag, which is why 9 is going to come up here. So you see that if you're testing it, that's where it moves up. And then we have the 9, 16, and 7, and that's where we get the zigzags there. So then that moves up in the middle. Okay, so we get to the end here. And when I run make splay test, I use the overloaded print operator that we did all the way back with binary search trees. And at each level, you can see the in order, pre-order, and level order and post order traversal. So we do it in the right order, we get to 7 and 9, and we see the level order traversal here. 9, 7, 15, I should, like, so now what's gonna happen is I would find 10. Let me play that. So 10 is gonna come here, and now it's gonna rotate up like that. And then I would do 18. Now 18 is not in the tree, but what it's gonna do is it's gonna move 17 up. Like that. And then 15 and 6. So 15 is all the way down here. And so now we have a zigzag, so it's going to move it in the middle. Do another zigzag, so it'll move it up in the middle like so. And then we'll have 6. So 6 find, it's demonstrating again. It's not there, so it's going to move 7 to the top. And then the last thing I did kind of as an example is what I've done is I've created a random number generator here in cacheexample.cpp. And then what I did is I created an array of 100 integer pointers using the new keyword. So part of this is to kind of review things that we've done in the past in the semester. And then I created a splay tree of void pointers. So what that does is that if now we're actually using that principle of locality that we briefly introduced in yesterday's lecture, but you'll go into in a lot more detail in the computer architecture course. And all the most recently accessed memory addresses will be in there. So what's going to happen is I iterate through and I'm putting in 0, 2, 4, 6, 8 as the values in the integers. And then I'm inserting int cache plus I. So there what I'm doing is I'm putting in the void pointer at that location. So what happens is it's inserting every 32 bits. And initially it's going to have that tree, just like I showed you, where it all goes in one direction. But then what's going to happen here is I go through I through 0, I do 10 random, I get a random value, and I say seeking, and it should find this location. And then it does contains. So what's going on in this line of code is that I'm saying, is it there? And then it's going to bring that memory location to the top of the display tree. So therefore, if I'm looking for that value or its closest friends, those are the values going to be at the top. And then I call this function that I wrote called print splay root. So in print splay root, I've printed the location of the value, and then I return the value. So when I return root val, that gives me the data inside the binary search tree node. And then I cast it to an integer pointer because it's initially a void pointer, right? So now we've told the operating system that it's an integer pointer. And then outside, just to kind of review everything that we've done early in the semester, I then cast it to a value. So now I'm dereferencing it, and it's going to print out the value at that location. So then I print out that value, and I say if that value, if returns the value, I say test passed, otherwise test failed. And so what's going to happen is if I run make cache example, it's going to randomly print these values out. I thought I fixed that. Oh, it's going to, I fixed all that stuff. Okay, so what's going to happen is it's going to print out the in-order traversal of the tree. And it should find 46, and it's passing all the tests. Okay. So does anybody have any questions? Okay, so the next thing I want to do, and I think this might be a useful lecture for pre-internship related things. So in a few of the project descriptions, there was a need for being able to sort multiple different ways. So there's consideration of a priority queue, but can I use multiple values to be able to consider how to sort things? And this is what a treep will do. So a treep is a combination of a tree and a heap. We're going to use heapified ideas, but we're going to do this in a way that allows us to be able to sort it in a certain way, but then give certain weights to certain values. And so up to this point, we've learned about binary search trees. We have divide and conquer. AVL trees have this strict balancing, and in the algorithms class later in your career, in your curriculum, you're going to see that the AVL tree is going to be used often in situations when you need a guaranteed log n of search time. But in real world application, you'll see red-black trees are used when a relaxed balance is good enough. And splay trees are good for amortized, non-uniform access to the tree, where we have a situation in which we're accessing certain elements or we have a non-uniform access, and the splay tree gives us benefits there. And then we've also learned about min and max heaps, which allow us to give a priority to sort elements. But as I mentioned a little earlier, what if we want to get balancing and priority? We want to traverse a tree that gives us a sorted value. However, there's certain values that I might want to give more precedence to than others. So for example, if I have A through Z, but I want the letter M to be towards the top of the tree, I would want to give M some sort of weight, as opposed to the letters C, D, and Q. We know that red-black trees have complex balancing mechanisms than splay trees, but splay trees occasionally have worst-case access, where you have to go all the way through to the bottom. We also know that heaps are not truly sorted, that we will always have the top value be the value we want in the max or min heap, and we have a heapified property, but if we went through, it's not sorted. So we are going to sort, but then we're going to heapify values based on a priority. So each node in a treep is going to have a value, and it's going to have a priority value. And we're going to call that a probabilistic balance. So we're going to say that a treep is a binary search tree in which each node has a key and a priority. Now, I do want to point out, because earlier when these data structures were invented, often key and value were used as synonymous, but that tends to confuse modern students because a key and a value is what the two terms that we use for a hash table. So in this case, what they mean by a key is they mean some sort of data. So what the tree will be sorted at, the tree, you can see that in a in-order traversal, you'll get A, C, D, F, I, H, and J. I mean, H, I, and J, excuse me. However, the other thing I want you to notice is that there are these priority values in each node. And so F is at the top of the tree because it has the highest priority of 75. And so C and I are lower in that their priority is lower, but it's still sorted. And A and D have a lower priority than that. So what you're going to see is that in each subtree, the priorities are going to have a heap property, but the way that it's sorted is going to be a tree property. So we'll combine those two together, just like tree and internship, we combine it to pre-ternship. We combine tree and heap into tree. And so let me ask you a quick question, quick thought question. If I made the priority of D 72, what do you think would be different about this tree? What would we want? How would the subtree here change? Let me press escape so I can see who's in and people in the chat as well. Yes. Very good, exactly right. So what's going to happen, and I bet that's what's going to come in the chat as well. So Fang Kong D becomes C's parent. Absolutely right. So both of you are correct. It would look like this. It would say D would be 72, excuse me. C would be 70, and then A would be 55. So what we're going to discuss a little later is that the probabilistic aspect of it is that we can seed a random number generator, and then over time, we can have, as we're inserting values, this priority be random. And so this randomized priority would allow us to have a randomized balance. And over time, we're going to see, and I'm going to show you through experiment, that on average, it's better than a red-black tree. So here I have a little bit of the history if you ever want to read into it. So data structures like splay trees and treeps are more modern as opposed to data structures like hash tables, linked lists that were invented in the 50s and 60s. Now we're getting to splay trees that were 1984. Treeps were developed in 1989. And so when Cecilia Aragon, so she was talking about how Treeps will use this probabilistic data structure, and we're going to get this average to good worst case performance. So when they say average to good, I'm sorry, average out to good worst case performance, what we're going to say is that we could have a worst case scenario where we insert 5 elements and the priorities give us this kind of ordering. However, over time, when we start inserting these probabilistic priorities, it's going to start requiring us to do these rotations and move these elements back up the tree. And so when we use a probabilistic tree, every single time we run the program, it will be unique. So it will be different every single time. If I run the random number generator start at a certain time, when I'm inserting these values, based on that randomly generated result, what's going to happen is we're going to have different balances in different trees, and that's perfectly fine. The value that's going to have the highest priority that we have assigned will still be at the top, and the crucial part is that this gives us a good balance. All right, so does anybody have any questions about this before we start going into how the insertions and balancing actually comes around? Let me check to make sure there's no questions in the chat either. Okay, so we do have a question in the chat. The priority values are random. So Hector, well, the way I'm going to present it in lecture is first I'm going to show you where we select the priority values. And then in the second example, what I'm going to do is we're going to show that the data structure is going to generate a random priority value in order to provide a really good balance. Did that address your question? Awesome. Okay, so in the Treep node, what I have is we have it's very similar to a binary search tree. We have the data itself, and then everything else is the structure around it. I have a double for a priority, and then I have a left pointer and a right pointer. When I call the default constructor, I just call the default constructor for the data, the default constructor for the priority, so it's 0. Then I have a left pointer and a right pointer that I initially null. Then I have this overloaded constructor where I'm creating this Treep node, and I have the data in and the priority, and then we use the member initialization list to initialize the data and the priority. Then I have a destructor, copy constructor, so meaning rule of 3 requirements here for the Treep node. And does anybody have any questions about that before I go into the actual implementation of the Treep? So in the Treep itself, the first thing I do in order to do the tree copy constructor is I go back and we use that same thing with copy tree. So with copy tree, what I'm doing is I pass the original node, and then I have the destination node. And so to review some concepts from earlier, we call that destination node by reference, so that way any changes made to that node are preserved when we go in and out of scope. So what I do is I make a new middle node. So I call this the destination node, and I call origin and priority in the constructor. And then what I will do is that destination node, I call origin and destined left, origin and destined right. So now what I'm doing is I'm creating the pointers all the way through that tree. Then I have a delete node, and here with deletion, does anybody remember the traversal that we would want to use to delete all the elements in a tree? So we have pre-order, in-order, level order, and post-order. Which one is the best way to go about deleting a tree? Does everybody remember? Yep, we have one response in the chat. Fankong is correct, post-order traversal. And the reason why it's a post-order traversal is we have to go down to the bottom and delete those elements out so we can maintain all of the links. Does everybody remember that now? Okay, so Fankong, you're absolutely right. It is a post-order traversal. And so that's what we're doing here. We go right, we go left. So we're getting all the elements that are low on both sides, and then we delete the current pointer. So here we're doing it, we're using our understanding of post-order traversal to delete the tree. So in the Treep itself, we initially have a root node that I'm just calling with the default constructor. And then in the destructor, I called that private method delete node in order to clean all the memory out when we're done with it. Then I have the copy constructor. I'm sorry, it's scrolling went a little funny, I apologize. So if the root's equal to null, we just return, we don't want to do anything else there. Otherwise, what's going to happen is I create a new Treep node with the data from the root, and then I call this copy tree method to be able to recursively do everything else. Then I do the same thing with the assignment operator. The only difference is I first check to make sure that this does not equal the address of assign, so that way we don't go through this whole process of copying itself. This saves some efficiency. I mean, this gives us some efficiency. But then the same thing, if the root's equal to null, we just return that. Otherwise, we go through that whole process again. All right, so we've constructed the base of the tree, but now we want to start applying what we understand about inserting. So with inserting, we want to insert like it's a normal tree. So we're going to go in order all the way down. And so what's going on in treep2.h is I have this method, and let me start here with the private method for insert. So part one, insert like a normal tree. So what we're doing is we're saying if the current pointer is equal to null, then we found the leaf where we want to insert. And we just create a new Treep node. And because we're calling cur pointer by reference, we're able to do this and preserve the change. Otherwise, if it's less than, we just say cur pointer left, value and priority. Else if value is greater than, then we go right. So we're able to just go through as normal. And then print that we found a duplicate. We see here that we just say it's already in the tree. So that's the first part. We've already gone over this with binary search trees. The second part is where we perform the heapification aspect. See, all of you correctly identified that in the event that we put it in there and the priority is higher than the parent, then we need to start performing these rotations and move it up. So we're recursively fixing the order, and in this case, we want the high priority to the top, so we want to think of this like a maximum heap. So the lesson that I wanted to convey in the creativity challenge is that the maximum and minimum heaps control how your algorithm works. In the standard template library, in the priority queue, it sorts it from highest to lowest. But when you are building your data structure based upon the sorted doubly linked list, the sorted doubly linked list put it in from smallest to largest. And there are opportunities to use that kind of data structure for a priority queue. Then you learn the same thing with max heap and min heap, that based on how you want your priority you want it to be max or min, you could implement different data structures to do so. So in this case, in the Treep, we are going to say that it's a max Treep, that the maximum priorities will be at the top. So first, I'm going to do the same thing as I've always done when we do these rotations. You always check to make sure that it's not null, so that way you don't run into seg faults. And then we say the value, if the value is equal to cur left data, then we check to see if the left child has a higher priority. So in this case, the current pointer's left child's priority is greater than the current node's priority in this case. So then what we're going to do is we create pointers to temporary parent and temporary left, and then we're going to do a rotation right. So we said the parent's left temp parent's left is equal to temp left's right. And then temp left's right becomes the temp parent, and then cur pointer is going to point at temp left. So basically what we're doing is we are rotating up like so. And then all of these other cases, we check to see the right child is not null and has a priority. So it's the exact same thing, except it's in the opposite direction, where it's a right child and the priority is higher, so we have to rotate. And so we see that. So this just basically allows us to heapify up. We kind of analyze that specific element and then move it up. When I do print in order, what's going to happen is you're going to see that I'm going to print the data and the priority. And I'm going to do the same thing for pre-order and post-order. Level order, right, before I show you level order, does anybody remember the data structure that we use to store the temporary values when performing level order or a breadth first search of a tree? Anybody remember which one we used? So when you're performing breadth first search, you have to store which node you're going to evaluate next, right? Does anybody remember? Yes. We had to use a queue. Very good. And I bet that's what came up in the chat. And FanCon correctly also says a queue. And so that's what's going on here with the level order. We created that void pointer. Now you could also say T star pointer and make it work. This was a design choice to kind of help students as they're reviewing this code. Remember, oh yeah, this is what a void pointer actually is. And so here I'm just getting the address and storing the tree root. I cast it to a void pointer. And then in order to cast it back, I'm showing that you would have a Treep node with the pointer there. But basically the same thing works. You pop it off and then you keep going until the queue is empty. And then here in the Treep, you have the assignment operator and insert. We just call the value and the priority. And then I go to the root node value and priority. So now it's going to traverse down the tree to find that specific location. And then it will insert it and then heapify up by the priority. And so in the overloaded operator, I just call print order, pre-order, in order, and level order to be able to print out the value and its priority at any given time. And so what I'd like to do is now let's walk through a process of solving this. So the first thing we're gonna do is we're gonna insert D with a priority of 60. So what happens is the root will be null. So we will have found that location that's to be per pointer is equal to null. So we just create the Treep node, create D with a priority of 60. Then we're going to do 75. So initially F will be a right child of D. Well, what do you think we need to do next? What's the step that we need to do here? Yes. Yep, we need to rotate so that way D becomes, F becomes the left child, F becomes the root, and D becomes the left child of F because of the priority. So now we're going to do the same thing. We have H and 14. H is greater than F, and 14's priority is lower than 75. So therefore, we don't do any rotations. The next thing is we now say C is 70. So initially we put it in order. And so now what do you think we're going to need to do? Yes. Very, very good. And then, let me check the chat here. C becomes D's parent, very good. So now what's the next thing we need to do? Is there anything else? Or are we good? I saw a thumbs up, are we good? Yeah, so that's what we are good. And the reason why is because 70 is lower than 75. So what you were gonna say? I'm sorry, what? Because D is larger than C. So we have to still maintain that ordering, just like in a normal binary search tree, but then we're moving 70 up. So if C was 80, then what would happen is C would become, it would be F with 75, and then D is between C and F. So D would be here at 60, and then we'd have H over here at 14. Does that make sense? Okay, does anybody ever have any other questions so far? So what's going to happen is now we're going to insert A with 55, and that stays put. So now I has 65. So this means we are now going to rotate. Okay, so let's see what's going on in the chat. So the initial insert is based on data value, and the trickle up is based on the priority value. That is absolutely right. The insert is based on data, so it must be sorted, and the integrity of an in-order traversal must print out the correct value still, but the trickle up is based on priority. So yes, that is absolutely right, Hector. All right, so 65, so this is a perfect case to address Hector's question. So what do we need to do here? So somebody else tell me what we need to do in this case? Yes. Yep. We're going to move I up. We're going to rotate. So now H becomes the left child of I. And now I stays put because 65's priority is less than F's priority of 75. So now we're combining all of these concepts together. So you can see that over time, if we were to put a randomized priority over time, what would happen is we'd get a very good balance. Yes. If H had a left child, then what would happen? So let's say H, so let's just say G7, right? So what's going to happen is I is going to become 65, and then H would become, would go down here, and then G would still remain H's left child. Do we have any other questions? Okay, so let's continue. So then I gets moved up here, and now G, but now we're going to put 80 here. So let's go, so somebody new, take, see if you understand this, and dare to be wrong. If you're wrong, it's okay, I'm not going to shame you. What do we think is going to happen here with G? Who wants to give it a try? I'll pick on somebody. I don't get an answer here in a moment. Okay, yes. Very good, absolutely right. So we've now moved G up. So who else wants to try? What's the next step that we need to do here? So we have G with a priority of 80 and I with a priority of 65. So what do we need to do? Yes. So here we have G is 80, right? And then we have I, 65, and then we have H as the left child of, very good, outstanding. So now we have another step. So first of all, let me put that in the animation. So what's our last step here? What do we need to do? We have one more step we need to do here. Yes, in the back. Absolutely right. That's exactly what's going on here. We now have G moved up to the top of the tree. So here we have trickle up using recursion. I've shown you that code already. And we just do the same thing with write. And so here I have make treep insert. And in this example, I have some code here that I'd like to show you. And in treep insert.cpp, I use treep2.h. And what I'm doing is I have generated the ordering of the treep with the priorities. So I've hard coded them. And in insert and print, I've called the treep by reference. I've passed the value and the double for the priority. And I'll say inserting value with priority, and then I insert, and then I use the overloaded operator to print the in order, pre-order, level order, and post-order traversals. So I go into So when we run make treep insert, it's telling me everything that we're doing, and it's showing me the level at every single stage. And so this is the result of the run. And in the slide, here we see that it says A, C, D, F, G, H, and I. So we have maintained the in-order traversal property. So we have pre-order, so it's G, F, C, A, D, I, and H. So we have the pre-order checked. Post-order will say H, I, D, A, C, F, and G. And then level order, we have G, F, I, C, H, A, and D. So now we were able to prove that our treep is working in precisely how we want it to. Does anybody have any questions before I continue? All right, let me press escape so I can see if there's any questions in the chat. All right, so now we've hard coded it. So now let's make it random and let's see if these proposed benefits that I'm suggesting actually come to pass. So the issue with the current design is that we hard code a priority, and we want to be able to see if we can do some data hiding. So getting back to this, one of these things that you're supposed to learn in the course is abstraction and data hiding. So we want to be able to create a tree and hide the priorities from the user until they print the pre-order, in-order, level order, and post-order traversal. So what's going to happen is in treep3.h, what we're going to see here is some changes. Let me scroll down here to the constructor, to insert, and we're going to see that insert, instead of passing a priority, I'm only passing a value. So if someone's trying to use a tree, all they care about is that I get some sort of value and then it's balanced properly, right? So what's happening is I call rand mod 100, and then I insert that generated priority. So I'm keeping the priorities between 0 and 99, but it's generating it randomly. So instead of passing the priority, that work's being done by the data structure. So all the user is saying is, okay, I want it balanced, I want it to be pretty good, and so here's a mechanism that we're going to use. And everything else in this data structure is the same. The private methods where we pass the priorities and then heapify, that's exactly the same as in the previous version. All we've done is made a minor change to provide some abstraction to the code. And so now what I can do is I am going to call insert random. That is insert random.cpp. And what I have in this piece of code is I've seeded the random number generator. And by the way, I want to give you a piece of advice. This is a common mistake for new programmers. When you're using random numbers, it's a common mistake to take that srand and put it inside of the call or insert. The reason why that's not going to work is because it seeds and starts at time 0, and the random number is based on the amount of time that has passed. So if you put that inside of the insert method here in Treep 3, right before rand, what would happen is it would be the exact same amount of time every single time. So as a result, what would happen is you would generate the same priority every single time. So that's why I have the srand in main as opposed to in, as opposed to inside of that insert. Now, another way you might be able to do that is to call the srand inside the constructor. The drawback is you're calling that seed for every single tree that you create. So what I've chosen to do here in insert random is I've called srand precisely once, and if I'm making multiple trees, it will still preserve that randomized property. So what happens here is I've created a character tree, and then I've inserted those values that we did in the slide problem. And I've abstracted the priority away from the programmer. And what's going to happen is I'm going to insert the value, and then I'm going to print the tree. So when I run make insert random, what we're going to see is that I have certain priorities, and we see that A is at the top of the level order. But if I run it again, we see that C is at the top of the level order because its priority is 77. If I run it again, we see H is at the top because the highest priority is 66. If I run it again, we see that G is now at the top because its highest priority is 97. And I could keep running this and I would get different treats every single time. Yes? Because it's based upon the time in the on the clock, right? So srand T0 returns the time that's currently in the clock in the computer, right? So it's based off of that. But if you start with that, it's that time minus that value. So that's why it's different. But it is somewhat random. It's called a pseudo-random number generator. It's not purely random. But then here we have the result, and we're getting that different every single time. Okay, and we can see, and when I have in the slides here a different result. And so what I've done here in insert random 2 is I've seeded it once. I've created a vector of 100 unsigned integers. I've initialized all of them to 0. So in this dynamic array, in each loop, I create a tree, and then I insert a random number. Then I get the maximum height. I have a method. Remember we did this with binary search tree, how to get the maximum height. We compared the height of the subtrees just like we did with an AVL tree. And what I'm doing is I'm getting the maximum height for this temporary tree. And so what I've done is I'm inserting 100 random values, and inside of this tree, it will generate probabilistic priorities. And so then what I'm doing is I get the distribution for that particular height. And then at the end, I print out the distribution for these values. So I say if a distribution at that location is not equal to 0, tell me the maximum height. And so what's happened is I'm going to create 100 treats. I'm going to insert 100 random values. And then I want the maximum height at the end of each of those treats. So what I'm going to do is I'm going to run make insert random 2. And so now we've done that. And what's generated here is the result, the height of the tree for 100. So here we had 10 trees that had a height of 8, 9 that had 443, 10 that had 1,789, 11 there were 2,768. So I apologize, this is not 100. I ran this 10,000 times. So that's 10,000 trees. And 12 had 2,421, and so on, right? It's all the way down, and the worst case scenario is we had a height of 19. So when we inserted 100 elements, we had 2 worst case scenarios, or it was 19. If I run it again, we have 10 that's the worst case of 18. But we see that that number 11 there is the highest again. If I run it again, we're going to see that again, 11 is the highest. So there's something that's going to be special about that number. I'm going to show you in a moment. So here I run it. And so for 100 random elements, the natural log, the log base 2 of 100 is going to come out to about 7. So then if we did the best case, what's going to happen is it will be 7 plus 1 because we have to account for the root. So therefore, in a binary search tree, our best possible tree that we could come up with will have a height of 8. And the worst case, of course, would be the 100 elements. So here we actually see that we never do better than 8. Does everybody see that? So that's why. So we have 18 cases where we have a perfectly balanced tree based on probabilistic probability. And we know that our AVL tree is going to give us 8 at the end when it has it all done. Now the red-black tree is going to be 2 times that natural log value plus 1. So it's going to give us 14.28. So that relaxed balance will give us about a worst case maximum height of 15. Sorry. And so what's going to happen here is the height of the tree is going to come out to 3/2 times the natural log of n plus 1. So we put in that number, 3/2 times 6.64, then we add 1, and that comes out to 10.96587. So the average case for a tree is 11. So that's why we see that when we run this experiment, that 11 always comes out to being the average case. And we know that for 14 and 15, that's where we're going to see our range of red-black trees. So I ran this experiment. So this is I've shown you this. So 95.82% of the treats had a better max height than the worst case red-black tree, and 98.5% had a better or equal to the worst case red-black tree. And so is about 11:15, Treep deletion. I have several slides on it, but let's take a guess. Let's see if you can all design this on your own. Combine your knowledge of heaps and trees. So I want to delete from a tree. I want to delete the root node. So if I'm deleting from a tree, what's the first thing I would do? In all the trees and all the steps, what was the first thing we did every single time? Very good, we get the largest value from the left, right? And then what do you think we do based on the heap? So the largest value from the left is at the bottom, which means it has a lower priority, correct? So what do you think we have to do? Yes, in the back. Exactly right. That's exactly what we need to do. So here, if I'm deleting F, I move D up, and then I see that C has a higher priority. So then I rotate it like that. And then I'm realizing that slide, I thought I had like several slides. Delete C, A up, D has a higher priority, like so. We delete A, 80, we get, sorry, there we go. So now we're going to delete G. So G is going to move up. We're going to move A here, and we see that I has a higher priority. So we are going to move I up and rotate. Sorry, this what should have happened here is that I-65 should have been, this is correct because you have to, so does everybody see what I'm going to do here? We still have to maintain the ordering. So we're going to rotate left like so. And that gives us the final result. And so the rest of the slide lectures are the code that does this, but it's basically like you've done before. So you delete, we then trickle up and trickle down, just like you're familiar with. All right, so it is 11:16. Just if no one has any other questions, then you are all dismissed. All right, so we have two, I'm going to address the questions in the chat as everybody's leaving it. Make it the new root, so Fang Kong. So isn't the previous column maximum height? All right.